All right, so today we're going to pretty much finish the topic of simple linear regression, and we're going to start discussing a more complicated case with multiple predictors, which we're going to call multiple linear regression. Okay, but one last thing that I wanted to discuss today is variable significance. Okay, so reminder. What we did in the previous couple of classes was we tried to build a model to predict the price of a used Toyota Corolla based on the mileage. So our target was the price and predictor was the mileage, right? So, oh yeah, and in the previous class I promised you to show another simpler way to calculate residuals, right? So reminder, what are the residuals? Residuals are errors, essentially, right? So here, and you all have scripts opened up, right? From the previous class. I posted the script online, so you should have it. So this is what my scatter plot looks like. And if I feed the line corresponding to my linear model, this is what it's going to look like, right? So I can see that most points are not on the line, which is normal. I don't expect them to be on the line anyway. And the amount of discrepancy between the point on the line and the actual price of the car is called an error, or, well, in more scientific, fancy way, residual, right? So what we did in the previous class was this. We calculated the residuals as the difference between the actual price of the Corolla, right, minus the predicted price. So before we did that, of course, we had to run this line right here to calculate predicted prices. We have 1,000 cars in the sample. We use the function predict, and it predicts for us 1,000 prices. And then we take the difference between the actual price minus predicted, and that's the residual, right? Now, another way how to do the same exact thing is this. So this was the hard way, right? Remember I told you, there is a simple way and hard way. So this was the hard way. So I'm going to say, comment here, simpler way to calculate residuals. And that would be, let me call it residuals 1. Residuals 1. Okay. Use the function resid. R-E-S-D, S-I-D, resid, which is abbreviated residuals, right? And all I have to do basically is call this function and send the parameter, the model that I've built. So my model is called Corolla underscore simple linear regression model, right? That's it pretty much. Okay. So simpler way to calculate exactly the same result. All right. All I do is basically say resid and residuals of that model. And inside, internally, the function calculates predictions, actual minus predicted, and keeps that all in the data structure called residuals 1. That's the name that I gave. Okay. So if I run this line, I should see no red flags, right? And if I plot residuals 1, okay, I should get pretty much same picture as what we did before. So we discussed that ideally, what's the indication of a good model? Ideally, half of your residuals should be positive, half of your residuals should be negative, right? And they should form the uniform cloud of points with an average of 0, because half positive, half negative, they kind of cancel each other out, with an average of 0. But you should see no patterns, no curves, no trends, and the thickness of residuals plot should be uniform everywhere, right? So this was our residual plot, and we discussed that first of all there is like conical shape going on, right? Which we called how? If you see that the thickness of the residuals is not the same. It's called heteroskedasticity, right? Not a good sign, heteroskedasticity, okay? That means that your residuals basically change variability. They're not uniform, okay? And secondly, I can see kind of a shape, right? A high density of points right here, and then on the left side all residuals are positive. On the right side, most of the residuals are positive, so I can kind of see the curvature, right? So these two things is not a good indication. And we kind of knew that this is going to be the case because this is not going to be an ideal model, because when we ran the summary, right, what was our kind of indication? What are we looking for from a good model? Hold on, let me make it, yeah. From the good model, we're looking for as high R squared as possible, right? R squared is kind of a measure of the model performance, right? So we discussed that if R squared is 1, that's ideal. If it's 0, that's on the other end of the spectrum, as bad as it can be, right? And everything else in between is kind of different measures of accuracy, right? So our R squared for this simple linear regression was 0.355, right? And we said this is not great, okay? All right. One last thing that we're going to discuss today is significance test for the variable. Okay. So let's go back to the equation. So here is my equation, right? I had it actually in the comment. The equation of my simple linear regression is price equals to 15,816. That's my intercept minus 0.063 times the mileage, right? True or false, ladies and gentlemen? The slope, negative 0.06313, seems to be awfully small and close to 0. It is, right? So here's what I'm thinking. Could it be that my model showed me some slope, negative slope, purely by accident? In other words, I got these 1,000 cars, and just by randomness, by the pure coincidence, okay, by the randomness of choice, I got this sample that shows me that, you know, as mileage gets higher, the price gets lower. So in other words, could it be that my slope is actually can be replaced with 0, and my model will be practically the same as this one, okay? So here's what we're going to test. I'm sure you did that in your statistics class. This is just a reminder, okay? Here's what I'm going to test. Hypothesis testing. Null hypothesis. The slope, how did we call slope? What's the letter that we used? mx plus b, right? Okay. So the slope, we have only one slope, right? So I'm going to call it b1. Slope for the mileage, okay, is equal to 0. And the alternative, let's see how much you remember. If my null says something is equal to 0, what's my alternative should say? Equal anything but 0 means that that b1 is not equal to 0, right? Anything but 0, not equal to 0, okay? So, reminder, in statistics, there is such technique as hypothesis testing, right? And hypothesis testing has two hypotheses, right? There is a null and alternative, okay? H0 and H1. So null statement and alternative statement are kind of opposite, right? What null is not, that goes into your alternative, okay? So this is what we're testing essentially in this case, okay? So this is a test for statistical significance. Statistical significance of a variable. So if I find that my null is true, if I find no evidence to support the alternative, what does that mean? Well, that means that in my equation, this is my equation, right? I'm trying to predict price as the function of mileage. So mx, we used m, right? That's what you told me. M is the slope, right? So sorry, it's going to be m1, okay? I was under false impression that we're using b as the slope. M is the slope, right? mx, so m1 times x, well, x is mileage, right? Times mileage plus b, okay? So this is what we're testing. So if I find in favor of my null, so not enough evidence to reject null in favor of alternative. So null is still true. And this is, by the way, how testing is done, if you remember, right? That every time when you start testing hypothesis, we assume that the null hypothesis is true, right? And we're trying to find evidence to support alternative, given that we believe that the null is true, okay? All right, so if I find in favor of null and statistically slope is equal to 0, that means that I can replace the slope in this equation with 0, in which case what happens? Whatever mileage is getting cancelled out of the equation, right? Therefore, I can say that mileage has no effect on the price, okay? Doesn't matter what price, what mileage the car has. If I can replace the slope with 0, 0 times the mileage is still 0, and the price is always going to be equal to the value of my intercept, right? So if I find that null hypothesis is still true, then that means, in plain English, mileage is not a significant variable, is not a statistically significant predictor. Statistically significant predictor. Okay. So this is what basically my null says. And the alternative, of course, is other way around, right? If I find that no matter how small slope m1 can be, it cannot be replaced with 0. That means that my equation still stays like this, right? Which means that mileage does actually affect the price, and therefore, if alternative is true, that means that mileage is significant predictor, and it must stay in the equation, okay? So we're going to actually use the same very test next week in order to find out which other variables may or may not be significant. But, so this is how we formulate the null and alternative, right? How do we test, how do we decide which we accept, null or alternative? Well, I'm sure we have some residual memory of p-value, okay? Each time when we formulate hypothesis, we need to compute p-value for this hypothesis, right? P-value. And then, what do we do? Remember? How do we decide which one to adopt, null or alternative? We compare p-value against what? No, that's against what? No, not confidence interval, no, not quite. Against significance level, right? So, against alpha. Alpha is like a measure of small probabilities, so to speak. Anything higher than alpha is considered to be not a small p-value. Anything less than alpha is considered to be small probability, okay? So, if p-value computed for the hypothesis is less than alpha, what do we do? Whoops. We reject the null, okay? So, if p-value is less than alpha, that results in rejection, reject null hypothesis in favor of alternative. That's how we formulate it, right? In favor of alternative, H1. Another way around is also true, okay? If p-value is larger than alpha, then we cannot reject alternative. Alternative hypothesis stays, okay? So we still believe it. We don't have enough evidence to reject null in favor of alternative. Do you remember these phrases from statistics? Do you send it, everyone? You should have done a lot of hypothesis testing in this course. Okay. So, essentially what I'm saying is, I need a p-value, right? Where do I find it? Okay. So, I find it in my output. So, here is my model summary, right? When I run this function, summary of the model, then it generates output for me. And let me tell you right off the bat that p-values are found in the last column where it says PR, probability greater than absolute value of p, okay? Last column. So the first column where it says estimate, that's where we find our intercept and the slope for the regression equation, right? In the last column where it says probability greater than t, that's the p-values, okay? All right. So, question is, well, even before we get to this question, let's find out what our p-value. So, do you see the first line where it says intercept? Intercept has a p-value at the end, right? You should see 2e minus 16, right? 2e minus 16. What does that mean, by the way, 2e minus 16? 16 zeros, right? So it's 2 times 10 to the minus 16th power, right? This is so-called scientific notation, right? Remember we discussed that, right? When we looked at the regression trees, we tried to predict actually exactly the same thing, prices of Toyota Corolla. And the prices were all expressed in like 28e plus 3, something like this, right? And somebody asked, like, how do we make it into the real number, into the actual number, right? Do you remember the answer? How do we make that into the actual number? We have to turn off scientific notations, right? And the way how we did that is this: options, SciPen, SciPen, equals 999. Let's do that, okay? So, if you run this line, SciPen, option SciPen equals 999, then it has no visual effect, right? But if I go back and rerun my summary of the model, now my p-value, you can see, is not anymore 2e minus 16, it's actually the real number, right? 2 and 16 zeros, right? So, here's my p-value, okay? Now I need to decide if it's higher than alpha or is it lower than alpha. But that requires me to pick alpha, wouldn't it? I'm comparing, let's go back to the hypothesis testing, right? How do I conclude hypothesis testing? I compare p-value against alpha. Well, okay, great. So question is, what is alpha? How much is it? What's the standard value for alpha significance level that is used by statisticians? 0.05, right? Now let me tell you a little bit more, okay? There are typically 3 different values that statisticians are using, okay? So let's discuss them, okay? So alpha equals 0.1, 10%, right? So if standardly, okay, if your p-value is higher than 0.1, that's considered to be large p-value. We have no evidence to support alternative hypothesis at all, okay? We're going to always keep null hypothesis, okay? If that is the case, if p-value is greater than 0.1, okay? Then there is a case when alpha, when p-value is between, it's lower than 0.1, it's less than 10%, but it's more than 5%, okay? So it's kind of small, right? Less than 0.1, but it's not very small. It's more than 5%, okay? So in this case, statisticians say that there is weak evidence to support alternative hypothesis, okay? To support H1, right? So p-value is kind of small, but not very small. All right. Then, going even lower, right? If p-value is between, whoops, so it's kind of informal way how we classify things, right? Remember we discussed similar approach to correlations, right? If correlation is between minus 0.3 and 0.3 close to 0, we call it weak correlation. And we have moderate correlation and strong correlation, right? So if p-value is between 5 and 10%, it's weak evidence. If p-value is between 5% and 1%, well, we're going to call it moderate evidence, okay? So standard value 0.5 is what statisticians are using, right? Anything less than 0.5, p-value is considered to be small. Above 0.5 is considered to be large, okay? So it's moderate evidence. Evidence to support, I'm not going to rewrite it, evidence to support H1, okay? Then if it's between, if p-value is between less than 1% but more than 0.001, more than a tenth of the percent, okay? This is, can you guess? Okay, the weak evidence, we have moderate, and this one is strong evidence, right? Strong evidence to support your alternative. And the last one, if p-value so small that it's anywhere between 0 and 1/10 of the percent, we call it, can you guess? Not strong, but super strong, very strong, right? Very strong evidence, right? Very strong. Okay? So this is kind of an informal way how statisticians divided the whole range of possibilities of p-value between 0 and 1.0 into these 5 intervals. So if it's above 0.1, that's it, nothing, right? We keep the null, nothing to even talk about. And then there are different gradations of strength of the evidence to support your alternative. Okay? How are we doing? Yay? Okay, cool. So I'm going to go back to my output, right, from the model, right here. And let me show you something. Do you see at the very bottom of your summary, there are significance codes. You see this line? That's a significance code, right? So the first one is right here. Okay? So if your p-value is between 0.1 and 1, that corresponds to our first case, which we just discussed, right? If it's greater than 0.1, then you will see nothing, empty. Okay? That means that the variable is not significant. Null stays. We don't reject null, and null says slope is 0, which means that the variable doesn't contribute anything to the model. Slope can be replaced with 0. Okay? Useless variable. That's what it says essentially. Okay? Now, if on the other hand, the next one, if your p-value is between 0.05, 5%, and 0.1, 10%, then you will see a dot. Okay, this one right here. A dot after the p-value, which means that there is a weak evidence to support your alternative that the variable is significant. Okay? Then the next range, as we just discussed, 0.1 to 0.5, 0.01 to 0.05, right? 1 to 5%. Right? Then we call it what? Moderate evidence, right? It's kind of standard approach. Okay? So if your p-value is between 1% and 5%, then you will see a star behind the p-value, which means that, yeah, it's normal. It's regular, moderate evidence that your variable is significant. Okay, let's keep going. If you are between 0.001, that's 1/10 of a percent, and 0.01, that's 1%, then how do we call this evidence? Strong, right? And you have strong evidence that the variable is significant, and it does contribute to the model. In this case, you will see 2 stars. In the last case, if your p-value is between 0 and 1/10 of the percent, that is very strong. You have overwhelming evidence to support your alternative, that the variable is significant. In this case, you will see 3 stars. Okay, so let's apply it to our case. Do you see 3 stars behind each one of our p-values? That means that our mileage is what? There is a strong evidence to support the statement that mileage is significantly contributing variable in that regression model. Okay? And one more thing that I wanted to emphasize, there is also p-value for the intercept, right? You see that? Intercept has the p-value. Normally it's reported by any statistical package. Okay, we can do the same analysis. R is not the only place, obviously, where this analysis is done, right? Same exact analysis can be done using our good old friend Excel, using SPSS, using Minitab, using SAS, any statistical package, okay? They will standardly report p-value for the slope, for the intercept, but it almost never tested in actuality, okay? So we're going to leave intercept out of this discussion, always. So we're going to only concentrate on the slopes, okay? In this case, slope for the only predictor, which is miles, okay? So we're going to always pay attention to only this one. And you can see that because the value is so small, it's 2 with 16 zeros in front of that. That is, of course, less than 0.1 of a percent, right? So therefore, there is very strong evidence that mileage actually is linked with the price significantly, okay? So it's not an accidental relationship that we have observed, okay? And that basically is the last portion that I wanted to discuss about the simple linear regression. Any questions, ladies and gentlemen? Okay, then let's continue. When we built this model, we kind of agreed that this is not the greatest model on the planet, right? Why? Because r squared is only 0.355, right? It's not huge. There is a room for improvement, obviously. How do you think I can improve the goodness of my model? More data is one thing, right? I can collect, instead of 1,000 cars, I can collect 10,000 cars, right? Okay, but am I guaranteed to have a better r squared after I collect more data? Or not necessarily? Yeah, it may improve, but it's going to be scattered all over the place, just like it did right now, right? So more data is one way, or what else can I do? I can say, well, mileage is not the only thing that affects the price, right? We discussed that number of accidents is important. Number of owners is important. It can be indication of the problem with the car, right? Type of transmission, manual versus automatic. What's the difference, by the way, in terms of mechanical reliability? Which is more reliable, automatic or manual transmission? Manual is more reliable, right? They break less frequently. Everything that's more complicated is more prone to breakage, right? So automatic is more complicated, it breaks more frequently, and it's very expensive to fix, right? Can the color of the car affect the price? It can, right? Extra features such as leather seats, sunroof, CD changer, built-in navigation system, all that can affect the price, right? So mileage, we saw it's a good predictor. By itself, it explains about 35–36% of what's going on with my prices, right? But 65% is still unexplained, okay? So, ladies and gentlemen, let's switch our attention to more predictors, okay? I'm still going to have the same exact target, price. That's what I'm predicting. Numerical target price. But I'm going to include all predictors in my model, okay? All predictors that I find in my data. So let me go ahead and start a new R script. And let's just do the same exact thing, right? So Corolla underscore data. I'm going to read the file. Read.csv from it's C data folder Corolla.csv. Alright. Hope it doesn't give me any problems. Okay. How do I build the model which includes all columns, well, except price, of course, as my predictors? Any ideas? I'm going to even call it same as I did before. Corolla underscore. I had simple linear regression. This time around, how I'm going to call it? Multiple linear regression. Because simple is one predictor, multiple is many predictors. Okay? Multiple underscore linear underscore regression. Okay? Alright, so which function do I use to build my model? LM, linear model, right? It's built-in function, LM. Alright, and what do I communicate to my LM function? Well, first of all, what's my target and what are my predictors? Well, my target is still price, right? Price. And what are the predictors? Everything else. How do I say everything else? Period. And then comma. And the other thing, I have to tell function LM which data to use, right? So data equals, well, Corolla data, obviously. Let's run it. It should give you no red output. And after that, how do I see my model? What do I do? Plot. I have to call the function summary, right? Give me the summary. Summary of my Corolla multiple linear regression. Now I have simple and multiple linear regression going on, right? Okay, cool. Bam. So now it has more members in the output, right? More lines, naturally, because I have more predictors, so therefore more lines, right? So I don't have just one slope, I have multiple slopes, agree? All right. So, ladies and gentlemen, let's first kind of talk about accuracy, right? Or goodness of fit. Is that a better model than the one that I had before? In general, do I expect it to be better or worse? Better, right? Because I include more, well, aspects of the reality into the model, right? I include more predictors, therefore, likely it will get better, right? And not worse. So, and you can see that there are a couple of r squareds, right? So far we discussed just r squared, as in there is only one r squared. Well, there are two of them, okay? They're fairly close in value, you can see. But one of them is called multiple r squared, and that is 0.8614. And there is adjusted r squared, 0.86. Later, next week, we're going to actually have a discussion what's the difference between multiple r squared and adjusted r squared. And the value that we want to use really is adjusted r squared, okay? We'll discuss why exactly next week. But they're fairly close, so what do you think? I used to have r squared 0.35, and now it's 0.86. Did it improve? Oh yeah, it did improve, right? So now it's fairly close to 1, so my model is PDG. Pretty darn good, right? Not exactly perfect, but fairly close. Okay, I'm pretty impressed with my model. Well, let's first of all write it out, okay? So for that, how do I do that? Let me go ahead and compress this thing right here. No, it doesn't work. Okay. Oh, you know what? I'm just going to put a bunch of empty lines here so that I can see it on the same screen. Am I genius or what? Okay. So, let me write out my equation of the model, okay? And now, actually, here's the kicker. True or false? Some of my predictors are numerical and some of my predictors are categorical. It is true, right? So, age, what do you think? Is it numerical or categorical? Numerical, that's months, right? Mileage, well, numerical, obviously, right? Horsepower, I'm skipping. Numerical, right? Engine volume, numerical. Number of doors, numerical. Weight, numerical. There is one that says automatic, so the cars can be either automatic or manual. That one is categorical. Color was weirdly encoded in this file. We only distinguish between metallic cars and non-metallic cars. Categorical, right? So we have metallic and everything else, like black, white, green, blue cars, everything is non-metallic. That's it. And there is another one, fuel type. But fuel type, now I see two fuel types, right? Which is weird a little bit, okay? In actuality, the column fuel type contained three different values, okay, for the fuel type. It was either CNG, compressed natural gas, or it was regular gas, gasoline, that's what we normally use, and another option was diesel, okay? But I see only two of them, right now. That's weird. So let's take care of numerical predictors first. So here is my equation, okay? I'm going to say my multiple regression equation. And there it is, okay? So, my target is price, right? Price equal. Let's take care of intercept first. Intercept is right here, right? I'm just going to copy paste instead of typing. How about that? And I'm going to keep 2 decimal points. There is no need for me really to have this killing accuracy. So here's my intercept, right? Minus 6610.06, okay? All right. Mileage plus, no, minus, right? Oh, age is the first one on the list, right? Age is minus, right? Minus 133.04 times the age. Okay? Mileage is also negative, agree? So minus, here's my mileage. Now this one I'm going to probably just copy paste entirely. Okay, minus this times mileage. Okay? Horsepower, 36.94, right? Plus 36.94 times horse underscore power. Okay, then what do I have? Engine volume, it's negative, right? Minus this one right here. just going to copy paste. This one times engine volume. All right, I'm going to start a new line. Equation continues, right? Number of doors, also negative, so I'm going to keep a couple of decimals only. This times number of doors. And I have weight variable right here. Again, a couple of decimals. And that's plus times weight. Okay? All right, so these are all my numerical predictors, right? Multiplied by their corresponding slope. So I have more than one slope now, right? More than one predictor. Each numerical predictor comes with its own slope, okay? So that should come as no surprise. All right, now we have to decide how exactly we're going to encode the remaining categorical predictors. And I have three of them, right? First, transmission type, manual, automatic. Second, color, weirdly metallic and everything else, non-metallic. And then fuel type. Fuel type has three categories, right? So, ladies and gentlemen, let's discuss categorical variable predictors, okay? So, in order to represent categorical variable in the equation of linear, multiple linear regression, we need to create something that's called dummy variables, okay? And this is how it works, basically. So, let's discuss the first one, for example, okay? All right. Let's discuss color, metallic. Okay, metallic. Okay, metallic has two options, right? It can be either 0 or 1. So R and R Studio, they take the very first category, which comes either alphabetically or numerically, and make it into the base or reference or benchmark category, okay? Base or benchmark category, okay? And that is the first one that comes either numerically first, numerically, or alphabetically, Okay, so in our case, metallic 0, 1, yes, no, right? Which comes numerically first? 0. That means that non-metallic, right? So in order to represent the color metallic, encoded as 0, 1, okay, we have to add to the equation two options, okay? 0 for the base category, if category is base, okay? And base basically means that metallic is equal to what? Which one is numerically first? 0, right? If metallic is 0, means that the car has non-metallic color, right? Then nothing is being added to the equation. That's plus 0, okay? And plus whatever is left in the equation if metallic equals to 1. Metallic equals to 1. Okay, so, and that means, let me go back, all right? This one right here, metallic equals to 1 corresponds to plus 42.63. Okay, so plus 42.63 if metallic equals to 1, right? So this is how it works always, pretty much. So we pick, if we're dealing with a categorical predictor, so here is the basic rule, okay? If categorical predictor has k categories, we need k minus 1 dummy variables. We need k minus 1, they're called dummy, quote unquote, dummy variables. Okay? So in this case, what do we have? Two categories, metallic, non-metallic, right? So we need only one dummy variable. K equals 2, right? 2 categories. Minus 1 equals 1. So we need only one variable, metallic. Okay? Which corresponds to metallic equal to 1. Right? So metallic equal to 0 is always going to be the base case. Right? So this is how we handle these categorical variables. So I don't know how I can type it here. Let me just go ahead and create a new line, and I guess I'm going to say plus, right? Plus here, if plus 0, if metallic equals to 0, okay, or else plus whatever it was. What was that? 42.63, right? 42.63 if metallic equals to 1. Okay. This is how I handle that specific case, okay, for this categorical predictor, the color. Make sense? Kind of, sort of? Yeah. Yeah, so I always use estimates from this column. That's essentially my slope. Well, in this case, when it comes to categorical variable, the word slope is not exactly applicable, right? Slope typically, slope multiplied by the variable, right? So there is no multiplication. Just basically says, if if you compare two cars, here is the real difference, real interpretation, okay? If you compare two cars, one of them, both cars are identical in all respects. Same mileage, same weight, same number of doors, same age, all the same. Except the difference is one car is metallic in color, another car is not, something else, let's say white. Okay, what do we expect? Well, we expect that metallic car will be 42.63 what? Dollars, because we're predicting price. Dollars, higher or lower? Higher than what? Than non-metallic. That's basically interpretation of this number. Okay, metallic cars are $42.63 higher price compared to identical but non-metallic in color cars. Okay, that's essentially what this means. So let's try the second one. Okay, similar variable. So another variable that we have, which also has two different categories, is automatic, right? So the car transmission type, essentially. Okay, so for the transmission type, what do I have to add? Exactly the same thing, right? Transmission can be automatic, in which case the variable automatic is equal to what? 1. Or manual, in which case it's equal to 0. So which case is base? Manual or automatic? Manual is base, right? Because it's 0 and not 1, right? So in this case, we don't go by the alphabetical, because in the file they're encoded as 0s and 1s, right? Fuel types are encoded as CNG, compressed natural gas, gas, and diesel. So in this case, we go alphabetical. But these guys, metallic, color, and the automatic transmission, they're encoded as 0s and 1s. So therefore, here we go numerical, right? So the base case is 0, which is manual, right? So what I'm doing is I'm adding to the equation plus 0 if what? If automatic equals 0, right? Which means, no, you're right, which means it's manual, right? If it's manual, right? And if it's automatic, what do I add? Exactly, the estimate for automatic. This one right here, right? $186.22. There. So I'm just going to copy paste. Okay. If automatic. Okay. So how do I interpret that? Well, if there are two cars again, identical in all respects, right? Same mileage, same age, same color now, both metallic or both non-metallic, whatever. Okay. Everything else being equal, the automatic car will cost $186 higher than identical but mechanical manual transmission car. Okay? That's basically my interpretation. Are we out of time today? Okay, so I'm going to stop right here, and then next class we're going to interpret the last one, the fuel type, right? And then we'll start messing with which variables are important and which are not so much.